Hello. This lecture is the first of 4 lectures on energy and the conservation of energy. This lecture will concentrate on defining what energy is and what work is. What is energy? Energy is like money. You either have it or you don't. And you can have different forms of it. Energy comes in many different forms: electrical, electromagnetic, thermal, chemical, and mechanical. We will focus on mechanical energy, which consists of stored or potential energy and energy due to motion, kinetic. But how do we get energy? Well, when we give something energy, we have to do work on it. Work can be thought of as the energy transferred into or out of a system. Work always involves a force and a movement through a displacement. For example, if you throw a baseball, initially the ball isn't moving and it has no kinetic energy. But to give it kinetic energy, you literally used a force with your hand and pushed it a certain distance before you let go of it. You did work on it, giving it kinetic energy. The definition of work applies when the force is parallel to the displacement. It is calculated using the formula work equals force times distance. The unit that we will be using is a Newton meter, also known as a joule. So in this example, a young man is pushing a box through a distance. If I wanted to calculate the work, I would multiply the force times the distance in order to figure out how many joules of energy the box is getting. To give you kind of an idea of how much energy different things have, for example, if you operate a 100-watt light bulb for a minute, you are using 6,000 joules of energy. It's equivalent to that much work being done. If you turn a page, it takes 1,000,000th of a joule to turn the page. Here's an example. A 50-kilogram block is pushed by a 200 Newton horizontal force on a frictionless surface. If it is pushed 5 meters, how much work is done? The formula in this case will be F times D. So we'll take our 200 newtons and multiply it by our 5 meters, which will give us 1,000 joules. What if we're applying a force at an angle, like when we're dragging a suitcase? The force is being applied to that suitcase handle. The tension, or F, in the suitcase handle is applied at an angle to the horizontal as the suitcase is dragged. So the force that's actually causing the suitcase to move straight across the floor is the x component, or F cosine theta. So when I multiply F times D, I really need to multiply F cosine theta to use the appropriate force times the distance. Because remember, in order to do work, the force and the displacement have to be parallel to each other. So that creates a new equation for forces that are being applied at an angle. W equals FD cosine theta. In example 2, a 100 Newton force is being applied to a rope held at an angle of 60 degrees to move the 50-kilogram box 5 meters. How much work is done moving the box? So in this case, the 100 newtons is not a horizontal force, but it has a horizontal component, F cosine theta, which means that we're going to use the FD cosine theta formula. Plugging in, we get 100 newtons times 5 meters times cosine of 60, which gives us 250 joules. So when we moved the box, which originally had no kinetic energy, we had to do work on it. And when we did work on it, we gave it 250 joules of kinetic energy as we moved it. Work can also be written as a dot product of the force times the displacement. A dot product is a way to multiply two vectors. In all our problems in our previous chapters, we've only had a vector times a scalar, like for instance, F equals ma. F is equal to mass, which is a scalar, times the acceleration, which is a vector. When you start multiplying vectors, you can get two outcomes. What we want is to multiply two vectors, in this case, to give us a scalar. Energy is a scalar quantity. It has no direction. You either have it or you don't. It doesn't matter whether it's east, west, north, or south. So in calculus, when we do this, we call this the dot product. And the way that you make sure you're getting the dot product is you multiply the horizontal component of the force times the magnitude of the displacement. Work done can be positive, it can be 0 or negative, all depending on the angle between the force and the displacement. That angle, if the force and the displacement are at theta less than 90 degrees, then you will get a positive work value, and that means you're transferring energy into the system. If the force and the displacement are perpendicular, when we take cosine of 90 degrees, we get 0, so the work done by that force will be 0. So if you're applying a force perpendicular to the displacement, it does no work in the system. It doesn't add energy at all. And if you are applying a force at an angle greater than 90 degrees, then the work will be negative, because think about it. The x component of that force is in the westward direction compared to the eastward displacement. If the object is trying to move east, but there's a force pulling on it to the west, it's going to slow down and it's going to lose energy. Thus, it has a negative work. If there's more than one force acting on an object, we can find work done by each force and also the work done by the net force. The total force is going to be the sum of the total work is going to be the sum of all the forces acting on the object. Here's an example. A 100 kilogram car sits on a 30-degree incline. Determine the work done by F parallel and the normal force if it slides 10 meters. So remember that F parallel is mg sine theta, where theta is the angle of the incline. So the work done is going to be equal to F parallel times d. So plugging in, I get mg sine theta times d, 100 kilograms times 10 meters per second squared. We're using 10 instead of 9.8 just to make our calculations easy for example purposes, times the sine of 30 times 10. Make sure that your calculator is in degree mode, and you should get 5,000 joules. But look at the normal force. When we plug into the work equation, work is force times distance as long as the force and the distance are parallel to each other. But look at the normal force N compared to the displacement vector. They are perpendicular to each other, which means that the angle between them is going to be 90 degrees. And when we plug into W equals FD cosine theta for forces at an angle, cosine of 90 is going to be 0. So the work done by the normal force is nothing. It's doing nothing to add energy to that car. The only force in this system that's adding energy to the car is the parallel component of weight. What now if there's friction in the system? So if I tell you that the coefficient of friction is 0.2, and I want to know what the work done by friction is, and the total work done on the car if it moves 10 meters, how do I do that? Well, first let's find the friction force. Friction on an inclined plane is mu times the normal force, mg cosine theta. So that's going to give us a friction force of 174 newtons when we plug in. The work done is going to be equal to the force times the distance, but remember they're both vectors. The force vector For friction, friction acts in the opposite direction than the displacement, so we can just plug in negative FF, or negative 174 newtons, times a positive displacement of 10 meters, which is going to give us a work of negative 1740 joules. What does that mean? It means that the friction force is transferring energy out of the system. It's turning it into something else, and we all know what friction does. If you rub your hands together, they get hot, because friction turns mechanical energy into heat energy, which can't be turned back very easily. So if I want to find the total work, I'm just going to take the work done by the parallel force, pulling it down, plus the work done by the friction force, slowing it down. 5,000 joules from the previous slide plus negative 1740 joules gives us a total work of 3260 joules. So the car is going to gain that much energy in the form of kinetic energy as it slides down the hill.